I'm working in this industry about like 15 years now. So I have seen around the globe that multiple operators that struggling and also spending millions of dollars to do the optimization and as well as to improve the network quality in their RAN network. So that is the focus. That is the target of my presentation today. What really this RIC, the RAN intelligent controller, can bring into the operators world, and what would be the future, or what would be the operators future would be look like with this the implementation with the RIC. My session has I would say four major areas of 4 sections. So let's start from some of the introduction of the RIC. We need to little bit set the ground and set the base, what is RIC and how exactly it's working, and also the key functionalities and the use cases. And the latter part, I will be discussing what is current, what kind of tests and what kind of deployments that we can see in the market, and the last section, what we are seeing, what we are predicting in the future, the deployment or the development of the RIC as such. And hopefully we can open 5 to 10 minutes for the question and answer at the end of the session as well. So let me start from the basics. So I believe like whoever who's following the Open RAN and also the Open RAN Academy is familiar with the Open RAN architecture. But let me highlight or set the ground a little bit right, which relevant to the RIC. So in the architecture that we have DU and the CUs. So DU and CU is the baseband components when it's come to the traditional architecture. And these traditional architecture components has been disaggregated in the Open RAN solution. So the main idea that you would have less components, less hardware close to the radio sites, and you can do a lot more hardware and a lot more functionality centralized in your centralized data centers, so that you get the pooling advantage and the hardware optimization. So DU called distributed unit, the CU called the centralized unit, and CU has also divided into 2 parts. One is the control plane and the other one is the user plane. When it's come to this application, the one part is the latency when it's come to the user plane. The other part is that your radio resource management, especially when you wanted to change or you need to indicate any change to any of these components, and if you are trying to make a change on these components, so we need to maintain some latency levels. So if you are doing some changes to DU, so radio resource management decision is usually within like 1 to 10 millisecond granularity. So you need to do the decision or the change of decision or the feeding of those decision within that granularity. And the centralized unit, it's handling most of the higher layer functionalities like the layer 2, layer 3, which is RRC and the PDCP layers. So you don't need that level of the granularities of the latency to maintain. So 10 millisecond to 1 second would be good enough for changing any RRM decision. So that is the latency target levels that we would need to maintain, especially when we are having discussing a little bit more in the few next slides. But if you are implementing RIC kind of solution, which you are trying to manage those elements or try to instruct those decision, we need to maintain this latency level. Over the years, especially in this traditional RAN domain, what we see, those RAN functions and the procedures, those are very, very much proprietary. Only the RAN vendor who could do the manipulation or the customization of their own RAN procedures. So that, and also there is only few successful other third-party vendors out there in the market who could discuss with this the big giant RAN operators or the RAN vendors that could cater their third-party application to do the optimization of the RAN. So they had to have like very close loop discussion, the integration and the development of their product, which made their product is very expensive and only target for very specific few use cases that who could intervene to the network and do the optimization. So that is where that if you have heard, like I'm discussing in my latter part of the slides as well, the self-organization network standards that 3GPP is designed. So even though they came into the picture, even though that they are mandating some of the information to be shared, there are only few successful use cases around the world that who are using those features as a SON implementation. And if you take some examples, or if you see it around the world, like those SON applications are used either in patchy coverage, like for example, to optimize some certain areas or some certain segment of the network, and also maybe that they are using, most of that they are using by the tier one operators who afford those kind of expensive solutions. So that's where the MNOs or the operators wanted some cost efficient and flexible network optimization. And to create that, they wanted to open up those procedures and also the reveal this black box and understand how this process is working. So that is where the Open RAN standards, while they are opening up the interfaces between the RRU and the DU and the in-between nodes, and the working group 2 and working group 3, real-time RIC and the non-real-time RIC, the working groups has decided, let's agree to a framework. Okay, these are the information that I'm sharing between the higher layer or with the third party, and these are the parameters that you can change via this interface, and come up with the architecture that is flexible for any third party to come in and provide the higher layer functionalities to do the radio resource management or the optimization. So that's where this RIC architecture comes. So let me let me discuss the key components to the RIC architecture. We already discussed the Open RAN elements in the downside of this picture, and we have one component called SMO, services management and orchestration layer. So this SMO is, if you really think, it is not really an Open RAN only component. So SMO is already there with the 3GPP world. If you take an small, the tiniest element of this SMO would be the element manager system of any of these RAN vendors. So they have their element manager. So that is part of the SMO. But on top, the SMO that with the 5G concepts, that there are some slice manager functionalities. And if you are in like the cloud-based deployment solution, then the cloud orchestrator or the Kubernetes orchestrator, this high-level umbrella orchestrator functions comes under SMO function. With the Open RAN and the Open RAN Alliance, that they added new component called non-real-time RIC into this architecture and inside the SMO functionalities. So what non-real-time RIC does is it gets the information from the SMO, which is the control management, the fault management, and the performance management data, like your PM and CM data, into the SMO, and via the R1 interface that it gets into the non-real-time RIC. And with the development of machine learning and AI, artificial intelligence components as well, so now embedded in non-real-time RIC, so you would be offline, analyze and learn all this data and come up with declarative policies. So when I say the declarative policies, it's mainly for the UE group level. Let's say this is the target throughput that you should target for this setup set of UEs. And the cell level declarative policies, this is the minimum RSRP value that you should have in one of these cells. So you can't, you have to maintain this kind of minimum RSRP values in this cell. So that kind of declarative policies would be transferred towards the either SMO or towards the near real-time RIC. So let's say if you are transferring that information or the declarative policy toward the SMO, so that would be more likely to be a configuration change. If it is, let's say as an example, if it is a handover, so then probably that the near non-real-time RIC is asking SMO to change some handover parameters, or the, like, let's say the threshold to trigger the handover to the next cell. So that kind of configuration change might be asking from the SMO to change into the DU or the CU. On the other hand, if it is towards the near real-time RIC, which is the other component of the RIC, that is mainly, that would be a policy that's setting up a policy, as I said, the cell level or the slice level kind of direction towards the near real-time RIC. So what near real-time RIC does is it caters UE level, the much more granularities. The UE level, it collects the UE level data, and also it performs more individual based activities towards the E node B. So let's take an example to understand this. So let's assume that you need to have you need to improve the latency of your network. Let's say that you have two use cases. One is URLCC, and the other case is the say mobile broadband. So non-real-time RIC gets the information and understand there are some of the issues in the network, and this particular some set of UEs in the URLCC slice doesn't get enough info. The performance is not really good. So he is giving a policy, or he is asking near real-time RIC, you better maintain at least minimum latency for this particular slice. So near real-time RIC now gets that idea, and then he's trying to implement. So he's assessing, okay, what is the current UE buffer levels? So which UE having worse RSRP, and which UE is having the better RSRP? So can I move this UE, say for example, that if you have multiple radio bands, let's say the higher bands and the lower bands, so can I move some of these UEs to a different band in the same E node B or the G node B, and which UEs that I can keep in the same cell or the same frequency? So that kind of real-time decision would be taken within like maximum 10 millisecond granularity by the near real-time RIC. So that's where the importance or the beauty comes with the combination of this non-real-time RIC and the near real-time RIC in Open RAN architecture. Also, you can see there are two elements I have mentioned here, RAPs and XAP. So I'll explain this one in the next slide. So RAP, what is this RAP and the XAPs? RAPs and XAPs are nothing but third-party applications that can run inside the RIC platform. So RIC platform could come from one vendor. Let's say Mavenir, we have both near real-time and the non-real-time RIC platform, which has that our own machine learning algorithm and the other logics that we have feed into it. And third parties can come up with their optimization applications is same as the what you are experiencing with today with iStore or the Play Store with Google or Apple, that you have different third-party application for different application, your the video calls or whether you are TikTok or so different application, different use cases. So same concept here. For the non-real time, you have the RFs. The real-time RIC, you have the XApp. So third parties can come up with their innovation. So more the third parties comes into play, it increase the innovation and increase the competition. So that reduce the proprietariness of the solution that we had in the previous, and also it fed away the premium that we had to, or the operator had to pay for specific solution that only come up with the proprietary world. And since that you can have your selection is high now with the multiple applications that you have, we are expecting that network improvements or the KPIs or the user experience would be much higher after implementing the RIC solution. So finally, the ultimate target is to improve the user experience and they reduce the OPEX of the operators. I thought a little bit is good to understand and a little bit benchmark what we are seeing so far as the this kind of RIC, I would say equivalent or RIC kind of functionalities. It's mainly comes in the 3GPP world, which we call self-organization networks. So self-organization network or organized networks also has different variants. We call distributed zone, centralized zone, and geo-based. So when it's come to the distributed, it is more individual. Especially it came up again from the RAN solution provider or the provider. These zone functionalities came in, so it wasn't multi-vendor or real-time granularity, and especially we couldn't do the third parties couldn't intervene of any of these zone functionalities because this came either from the radio vendor or the specialized vendor who could hand-in-hand work with the proprietary solution provider. And the other major part is the UE level measurement. With the 3GPP release 10 that the 3GPP introduced this MDT, the minimized drive test, even with that, the solution that we see is very limited, that you collect in the UE level information and productize it as an optimization solution. So the best way so far, what we collected the UE level information is the drive test. So there were lots of drive test companies and the tools that facilitating collecting UE level measurement. But anyone who has involved this drive testing and the optimization process, it is very expensive and time consuming. And you require specific knowledge to analyze all this data and come up with a solution to do the few solutions to improve the network. Even you do that kind of improvement to your network, you need to implement, and then you need to check, say have a grace period and see whether this solution is work or whether there is adverse effect, and then probably the roll back to the previous parameters that you had rather than implementing new parameters. So all this, what I'm trying to highlight was patchy solution, extensive and the tiresome solution with so much money involved. So that is where that again this RIC come into play. So you are collecting lots of information, especially with the near real-time RIC, you are collecting UE-based information and you are adding those AI machine learning functionalities. So now as much as data you have, as much as training that you can do to this machine learning algorithms, that you can get the higher and higher performance. So every day, this platform, this learning would be getting mature and experienced enough to provide the superior level network optimization towards network. So let's discuss a little bit about the things that we can collect and the data that we are negotiating between each interfaces. So first, let me highlight few of the buzzwords or the standard terms. So I'm talking here regarding mainly the near real-time RIC. So near real-time RIC talking to the DU and the CU, so the baseband via E2 interface. The protocol that E2 interface using called E2AP, which is also called E2 application protocol. On top of this E2AP, there are some policies or the contract that accept negotiating with the E2 nodes to understand, okay, these are the information I need from you. Please send me in this kind of periodicity that I'm going to use this information for, to do this kind of control. So this kind of agreement is setting up between the E2 nodes and the XApp inside the near real-time RIC. So that policy or that contract called E2 service model. So there are three major service models. One is to collect information. We call it E2SM KPM, key performance measurements. And then the other one is the E2SM RC, the more towards that how we do the control towards the E2 nodes. And there is the other one called the E2IN, E2SM-IN, which is the interfaces. So here I'm showing more of the what we can collect. So that's why that most of these elements end up with E2SM KPM, which is the measure. These are more about measurements from collecting via DU and the CU. So I wanted to highlight, so this is the level of information that we can collect. So we can even collect the PRB utilization from the cell wide and also the number of UEs that connected to the cell. And more importantly, that UE specific measurement like RSRP, RSRQ. So those are the key measurements that we did earlier using the drive test. And we can understand what is the modulation level that those UE has. So now the RIC has all this visibility towards the detail level information, the cell level, as well as the UE level to analyze, to make the decisions towards the E node B or the baseband, or ultimately towards the UE. This is the, if you consider the control part of the E2, which is that what we can change when it's come to the DU and the CU. So we can change the radio bearers. So that means that the bearer QoS level. That means like if it is a UE, if there is a UE that has good RSRP or the good radio receiver levels, but currently he is having only bad quality of service. So then near real time RIC can understand it, and he can allocate the new bearers with higher QoS level to that particular UE. And also the scheduling parameters, like how many PRBs that I should allocate in the uplink for that set of UEs or that particular UE. And when it's come to especially the mobility control part, if there is a UE that get a neighbor, if get the service from a neighbor, and also that currently serving from some other base station, and maybe it is there when we need to do a handover, there are some certain threshold has to meet. So there are some parameters that we need to trigger. That's some UE to perform a handover. But there are some occasions, and we get, even though we don't trigger those handover parameters, but still that UE gets a good coverage from your neighbor cells. So those kind of situation that you can identify by the near real-time RIC and immediately can transfer those UEs to the new cell to give better performance. So this kind of intervene and the UE level actions can be taken by the near real-time RIC via the other part is the O1 interface. So the O1 interface mainly interaction interacted by the SMO. So he mainly collects information from the performers, like the row counters from the DU and the CU. So as you may have understand that when we are performing the network KPIs, you collect the say call number of drop calls, the number of call success rates, the data rates of the collective, the data rates of that particular cell. So those kind of PM measurements are collected by the SMO and feed into the non-real-time RIC. And based on the non-real-time RIC decisions, that it can come out as a parameter change or the configuration change towards either DU or the CU. So the one of the good example is easiest example to understand is the handover parameter change, where that you are setting up few of the some DB values that you need to trigger, that if you want to do the handover, that you need to your neighbor cell signal need to be, let's say, better than 3 dB, better than your current signal. So probably that configuration management is indicating now, no, the 3 dB is not right. Probably you can change the you can change it to the 4 dB. Or maybe if it is a coverage optimization kind of procedure, probably that if your network is supporting, let's say, the electrical tilt of the radios, probably that you are sending a message to that system, your antenna has to be a little bit tilt, maybe 1 degree or 2 degree tilt downward to give the best optimum coverage. So that kind of configuration change could be the output from via the O1 interface towards the network. The new interface, the interesting interface is the A1 interface, because this is where that you are discussing between the near real-time RIC and the non-real-time RIC. I earlier mentioned, so the non-real-time RIC is mainly come up with declarative policies. So let's understand this in some kind of an example. So if you are familiar with any sport, let's say cricket, rugby, or the basketball, so you have a team that play in the ground. So the captain and the team players, that they are making real-time decision at the game, at the ground. So that's more equivalent to near real-time RIC. So based on the information, based on the game, that the way that you read the game, you are making decision to improve your game. But you have coach and some of the tech advisors in your dressing rooms, that who are analyzing the game and the high level. Maybe those coaches and those tech team has some previous data, the how the opponent has played previous game, and the analysis of their opponent players and their game. So then the middle of the game, that the coach might be signaled to the captain, you need to change the game. So maybe that you need to change the game a little bit in this way. So that kind of declarative information is coming from non-real-time RIC to the near real-time RIC. So that is what I take the example earlier. So let's say the slice level information or the cell level information. This is the minimum RSRP for this particular cell that you can maintain. So then non-real-time RIC has to decide, let's say that if you have a dual connectivity solution, you have the leg, LTE leg as well as the 5G leg. Probably you can move some of the UEs to the LTE while keeping some of the UEs in the 5G leg to balance the traffic between these the two technologies. That makes the improvements of the throughput or try to maintain the direction that non-real-time given to the near real-time RIC. So that's the communication happens via A1 interface. Let's try to understand all these concepts in kind of overall with an example. So we have our Open RAN elements here that we have discussed. So this is open, and now we have our non-real-time RIC and the near real-time RIC. So assume this base station is in a stadium, and we have normal, say, low band 700 megahertz band in allocated for this radio, as well as that we have massive MIMO 5G radio as well in the same stadium, focus in the same subscribers. So now, during a game or during in activity happens in this event, the non-real-time RIC is collecting information, and also probably that this data lakes, this database called as data lakes, might have previous game or the previous stadium information, and your machine learning algorithms has already trained to a scenario that especially the traffic scenario in kind of this stadium. So you have developed a particular app, R app, in this non-real-time RIC to handle this stadium traffic balancing. So now you are collecting those information and feed back the SMO with the relevant information. So as I said, could be let's say he has identified there are some users who are serving by the massive MIMO radio, and it would be better that if I can move this person to the other band and push back to the manage the traffic between these two bands. And also the same information would be feed back to the near real-time RIC, and now near real-time RIC is getting the real-time information from the DU and would be deciding which cell or which UEs that would be better to transfer into the massive MIMO or either to the lower band, the 700 band that as per the example. There could be some users who really require like uplink who are posting in the Facebook, and there would be some users who are really doing the VR like augmented reality or the virtual reality kind of application to get the real-time game information in this stadium. So then you need to balance like uplink PRBs versus the downlink PRBs, and probably that you need to allocate multiple pencil beams from the massive MIMO towards the particular users, I would say. So this kind of scenarios happens together with SMO near real-time and non-real-time RIC together to improve the user performance. So let's talk about what we are experiencing or what we have as use cases today, what we see the initial use cases together with RIC. So these are very popular non-real-time features, and these are also very common when it's come to the self-organization networks or the SON networks as well. So what we see that even today, the non-real-time RIC is starting with these features, especially the coverage and capacity optimization is the key. So you would be collecting the information from the cell and try to come up with the best configuration and indicate towards the configuration management. Okay, these would be the best set of parameters that we can manage for this particular cell to improve the KPIs for this particular cell. The other part is the mobility robust optimization. So focusing on the handovers. So there are a set of parameters that we are targeting when optimizing handover between two eNodeBs. So like we call A3 event and A3 offsets, and the hysteresis value that trying to keep a buffer to not to happen ping pong values, and also the some of the timers that we have to make sure not to happen ping pong handovers. So all this that collecting the information based on the failures of the UE handovers and also the success rate of the handovers, and based on the machine learning, the learning or the train model that they can implement these. And the other one is the load balancing. So you would be experiencing high number of UEs in a cell, and while that you have very low traffic in the other cell. So it would be easy to understand those the capacities and the number of UEs available on those cells, and direct the DU and the CU to transfer these UEs or the handover to the other cell to balance the traffic. So the difference what we see compared to the self-organization network, and as well as compared to the RIC here is this CCO that you can come up with, like you don't have to like different functions for the CCO and MRO. So probably someone can come up with RAP that cater both those functionalities and also the load balancing as well. And maybe someone else can come up with even combining, let's say even you are combining the mobility load balancing as well as that let's say energy saving functionality, that you understand the capacity, you try to move that UEs to different cells, and maybe that you try to turn off the massive MIMO panels in some of your radios. So that saves the energy while you are meeting the capacity when you don't need much capacity in, let's say, in the night time. So the possibilities, permutations, and the innovation is enormous that you can come up with. But at the moment, what we see is like the basic use cases that with the initial RIC for the non-real time that we see that operators and also the providers are the vendors are coming up with. The other solution, another example that what we are seeing for the near real-time RIC is the machine learning based traffic steering. So this one is quite important. So there are multiple use cases behind of developing these use cases. One is that the autonomous vehicles, especially traffic fleets and even the mining, that you have lots of autonomous drivers, and the coverage is key for this the automatic vehicles. So maybe you maybe some cells that you have lots of vehicles overloaded, and there would be some free up cells that you could immediately transfer those UEs or the vehicles into those the vacant cells. And also that if the network is see a kind of coverage hole or coverage gap, that you could take the measurements that you can you can target or the direct, if you have especially the red, the electrical tilt kind of solution, that or the beam forming kind of solution, that you can direct a pencil beam towards that UE to make sure that it doesn't lose any coverage. So that is one of the key aspects that industry is looking at as a very uh, a use case that would be implemented very soon in the near future. So let's see some of the results to at least to compare and understand like what is the maturity levels that we are having and what we are seeing especially. So this is one of the test the demo that we did 2021 with one of the operator functions. So that we implemented this the machine learning based handover functionalities, the traffic steering functionality, and we had some simulators to mimic the number of users and the scenarios. And what we understood using those machine learning based X app could improve the 28% downlink throughput and also the 28% handover performance. So this is what we are seeing with our initial testing, that traditional the improvements could be massive real-time improvements that we could improve, we could see in the future implementation. So these are like, this is 1 year back. So the solution, Navania and everyone else are getting much more mature, so that you would be experiencing much more improvements in the future. Similarly, I mean, if you tune into some of the recent press releases that Mavania did, so we are working with some universities to do the prediction and the simulations, especially when it's come to the RIC. This is one of the activities that we did with them, and to compare some SON solution together with our RIC solutions. So what we are seeing those simulation is RIC always, like sometimes even 40-50% is better than normal radio resource and radio management. And the SON functionality, SON features are not that can close to the RIC performance levels when we are analyzing those performance compared to those SON when we are comparing to those SON solutions. So you can see some of the PRB downlink PRB usage and as well as the spectral efficiency and the UE mobility overhead. So these are only few different areas that we have tested or the simulated, but we are seeing very good promising results towards future. As we discussed, what we're seeing is like very initial use case, especially that we are seeing the SON based features or the few XAP based features are available today in the market. But and also that the other thing is those XAP RF, XAP and the RF are a little bit mutually exclusive. So there is only individual RFs and individual XAPs. But what we are expecting in future, especially the future use cases are complex. So especially when you want to deliver the personalized service and the custom experience, especially cloud VR games, and the multi-access and the traffic steering, beam forming kind of use cases, you have to have the XApp and RAP combined solutions come up as use cases. And the other areas that we are seeing as the RIC would be contributed to the new revenue stream, especially optimizing the indoor coverage and the RAN SLS, because the indoor coverage is a vast area, vast segment of network that we didn't tap properly. Implementing the in-building coverage solution is massive cost, but there are lots of coverage optimization we can do from the outside of the buildings even. And also, even though we have the in-building, probably the handovers between the in-building and the outside macro coverage, we can optimize massively. So then that what we are tapping is the new customers, new revenue streams for the operators. The other part, the energy saving, the RAN sharing kind of application use cases would be reduce the capex and opex immensely. So there would be lots of involvement when it's come to the RIC, the implementation of these use cases. If you see some of the analysis, there are only few analysis and the surveys that we can found for RIC in internet. So this is one of them. So we can see that majority of MNOs are waiting for this. So they wanted to have this, and they would be they wanted to use this more for QoS based radio optimization, dynamic spectrum sharing. That you can see that 80% of the operators that they wanted to have this for dynamic spectrum sharing and the real-time video optimization. So those are the areas that we see that would be popular in future with the operators. And when it's come to the market, so this is another analysis from the mobile experts. So we are seeing this would be a growth of like by 2026, it will be more than $2 billion market that we are talking about, especially the RIC software revenue, as well as the XApp and the RAP software revenue. That would be tapped a huge market and huge business and open up lots of opportunities to the third parties. Probably this would be my last slide before the Q&A. So this is, I wanted to give kind of the futuristic use case. This is actually, even though it is futuristic, this is happening now. So it is not just the Open RAN. So the RIC would be focusing on or the assisting do the optimization or the improve the network quality end to end. For example, that you can pass the learning from the RIC, from the machine learning data lakes towards the EPC machine learning function, which we call the NWDAF. So then you can, NWDAF can work hand in hand with the RIC to optimize. Let's say if it is a URLCC slice, same as the radio network, the NWDAF also has to, the 5G core also has to allocate their slice according to the RAN requirement. And maybe that you need to allocate proper buffer sizes or the proper data packet sizes or the bearers according to the radio network requirement. So it would be not just RIC in the future, it will be end-to-end that learnings and the machine learning and the intelligence would be spread across the end-to-end, even towards the applications.